single phase full wave converter with R load. So today we'll be seeing the analysis, seeing the working principle for RL load. But since the diagrams or the waveforms and the diagrams are going to be a little bit difficult to draw, now I'm going to directly simulate the circuit with the MATLAB platform, and I'm going to explain the working principle based on the waveforms and waveforms that we get from the MATLAB. Because yesterday itself, myself, from my side, it's difficult to draw the sine waves, mark everything. So let me show the waveform in MATLAB itself. Then during the average voltage derivation and for the RMS voltage derivation, we will come back to the So let me share the screen, and we'll be seeing the screen is visible.
Yes, sir.
Whether the MATLAB screen is visible or not? Someone reply.
Yes, sir. Yes, sir.
Bharat? Okay. So the diagram shows you the single phase full wave converter circuit, power circuit with R load of 150 ohm. Right. So you can take time to draw the circuit if you want. Right. So I'm going slowly. So the circuit shows a full wave converter, full converter and full wave converter, whatever maybe, and you have the load is purely resistive, and the load is connected. The load is 150 ohm pure resistor, and 4 thyristors are placed in the bridge circuit, and it is named as T1 and T3 for the top thyristors, and it should be T2. And T4 and T2 for the bottom one. And I have, so in this circuit, it is we have discussed the thyristor T1 and T2 should receive similar pulses or identical pulses, and T3, T4 will receive identical pulses, right? Which will be complement to the pulses of T1 and T2, right? T1 and T2 will receive the identical pulses, and the next set of pair T3 and T4 will receive identical pulses, but these pulses will be complementary to the T1 pulses, or 180 degree shifted to the T1, T2 pulses. This concept we have already seen in the class before the lab, during the lab introduction class, and to have such pulse pattern, I have generated the pulse with the help of pulse generator block here, and you can take a look at the parameters that I have fed in the block. Here, as this is a simulation, the pulse amplitude is not a matter. But in practical, we know the pulse amplitude matters a lot. It should have minimum amount of current to trigger the thyristor. But as far as the simulation is concerned, the pulse is considered only as a signal, irrespective of the magnitude value and the duration of the pulse. If it is signal high, logically high signal, it will be considered as a proper triggering signal for the ACR. So in this context, so the amplitude of the pulse is taken as only just 1 volt, and the period of the total period of the pulses, the total period of the sine wave, which will be 20 e power minus 3. That is the time period. But what should be the pulse width? It is 50% of the period. So, but it need not be 15%. It can be only 20% or 30%. So I am reducing it to 30% of the total period. It means that whenever you trigger it, from that instant, 30% of the 20 millisecond, you calculate it. So 30% of the 20 millisecond, that will be the time period of the pulse, and that will be the width of the pulse. And the last parameter is phase delay, right? And this phase delay gives us the alpha value. Can someone say what is the phase delay for 3.3 millisecond? Someone tell me what is the phase angle delay for 3.3 millisecond? I asked what is the pulse, what is the phase angle, sorry, what is the alpha for this particular value of delay? $30. Okay, let us see what happens. So, and the first set of pulse T1 and T2 is delayed by 3.3 millisecond. So obviously the next set of pulses should have 180 degree further delay. So 180 degree corresponds to 10 millisecond. So the next set of pulses are generated with the phase delay of 13.3 millisecond. First alpha for the first set of pulses are 3.3 millisecond. Now this is 180 degree shifted. So obviously 10 milliseconds should be added with the previous one. So 13.3 millisecond is the phase delay, because phase delay is always calculated from the same origin, right? We are not detecting here, we are not detecting any zero crossing, nothing we are doing. We are directly giving the phase delay here. So if you are not measuring the second zero crossing, then obviously you have to take the first zero crossing as a reference. From first zero crossing, the pulses for T3 and T4 should have 13.3 millisecond delay. That's what it has been given, and a single phase power supply has been taken where the frequency is 50 Hz and the peak amplitude is asked, so it is 325.26, which means that the supply is capable of giving 230 volt RMS. That is the condition of the circuit. Now I am going to simulate it for just for 0.1 millisecond. The simulation time is just 0.1 millisecond. I am going to simulate. Let us see how this is giving us the results. So see the voltage and current waveforms here. And the top one is current and the bottom one is the voltage, and I have simulated the circuit for 0.1 seconds. 0.1 second, and if you look at the alpha, now you can understand that you see the first diagram, you see the first waveform. I am just showing you only one cycle here. Now I am just showing only one cycle, and see that the waveform is not 30 degree. What is the firing angle now? At least tell me, someone correct, tell me the correct value of firing angle from this waveform. From this waveform, can someone tell me what will be the firing angle? What is the firing angle? Say don't message, right? Unmute and tell me. I cannot keep on switching my screen. Don't type the message. You can unmute and tell me what is the firing angle. At least from the diagram, can someone give me the value of firing angle? Point 0035. What is that? I told you don't message me. Unmute and tell me. Unmute and explain how you have calculated the firing angle in terms of firing angle, in the sense it should be in terms of degree, right? What is 0.0035? This is why I always oppose this online class. 40 people are there, no one is responding, then why should I shout here like a mental students? Okay, that's all. This is a waveform, right? And when you increase alpha, you can see the waveform will change, and the average will be changing. So you can see the average voltage of the, you can measure it. You can measure the average voltage. Let me measure and show you two different for different values, to try to understand how the average voltage is changing. So I'm going to measure both the RMS and as well as your average DC voltage across the load terminal. For the voltage, I am measuring average and I am displaying it with a in this, and for the same value, same voltage signal, I am measuring RMS also, and I am displaying that waveforms or value also, not the value. So frequency is T. So let me simulate it again so that you can see what is the average value and the RMS value here. You can see the average value is 155 and the RMS is 205. If you can check with the formula in the whatever we have seen in the yesterday's circuit with the R load, average voltage is Vm by pi 1 plus cos alpha. This is the formula that we have seen yesterday. So the firing angle, I don't know how many of you have understood the firing angle concept. And the firing angle is almost 60 degree. So cos alpha, alpha is 60 degree here. And if you calculate in that aspect, cos alpha cos 60 is 0.5 and 1 plus cos alpha 1 plus 1.5. And we have VMS 325. VMS 325 and then divided by pi. So I am getting exactly 155 volt. Right, VDC I am getting exactly 150 where volt for alpha is equal to 60 degree. Right, because the time period delay is 3.3 millisecond. So the alpha is 60 degree and for alpha is equal to 60, I am getting exactly 155 degree. In the similar way, if you substitute alpha as 60 degree in the RMS value, you will get the exact value of 205.7. Right, this is for alpha is equal to 60 degree. For the same circuit condition, now I am going to change the triggering angle to 30 degree. Alpha as 30 degree. So let us see how the RMS voltage and the DC value voltage, DC voltages are changing. For 30 degree alpha, the delay should be 1.66 millisecond. It should be 1.66 millisecond. So I am changing this as 1.66 millisecond, and the complement pulsar should be 180 degree delay. So it should be 11.66. It should be 11.66. And now with this new alpha, I am simulating the same circuit without any change in the circuit parameter. Load and load is the same, 150 ohm and everything is same. Let us see how the voltage is changing. Before that, we will try to calculate the what will the average voltage for this particular condition. When alpha is equal to 30 degree, cos 30 degree is 0.86, so 1.866. I am getting 193. Average voltage as 193. Yes. So you can see here, this is 192. It is showing 192. Right. So when you decrease alpha, it is clear that the average voltage is increasing. When you decrease alpha, the average voltage is increasing. So vice versa, when you increase the alpha, the average voltage will keep on decrease. Even if you increase it beyond the 90 degree, and the alpha, that alpha ranges here, alpha is equal to 0 to alpha is equal to 180 degree, you can change it. From 0 to 180, you can change the alpha, and when you move from 0 to higher values for any alpha, then the average voltage and RMS voltage will decrease, right? And earlier RMS also around 205, now we are getting 225 volt RMS, right? From this, it is clear that when you reduce alpha, voltage is increasing. This is a condition for the R load, right? This is a condition for the R load. You can see both voltage and the current waveform. Current and voltage waveforms are very much similar. The only difference is the magnitude. The voltage is having the peak value of 325 and the resistor is 150 ohm. So here the peak value is around 2.3 ampere, right? And since it is a resistive load, the waveform is the current waveform is in phase with the voltage, and it is very identical to the voltage waveform. Only thing, the magnitude is little bit different. That is decided by the voltage value and the resistor value. But rest of apart from that, the pattern of the waveform is pattern of both voltage waveform and current waveforms are very much similar here. And now, if we see the if we go to introduce RL instead of R, I am going to use here RL. So now I am having 150 ohm resistance and 40 millihenry inductance with the same 30 degree firing angle, right? The firing angle is not changed. Earlier, please note it down, with 150 ohm or R load, we got 192 volt average DC voltage and 225 volt RMS across the load terminal. Voltage is supply voltage is same, alpha is also same. Now I have introduced an inductive element of 40 millihenry in the load. That is the only change that we have. That's the only change we have done. Right. Let us see how the waveforms and the average voltages are changing. After checking this value, we will go to the derivation. Our circuit is same, firing scheme is same, supply voltage is also same 230 volt RMS, but apart from 150 ohm resistor load and inductive value of 40 millihenry is added. Now we got a small reduction in the voltage, right? A small reduction in the voltage. Instead of 190, we got 191.6. Small reduction in the voltage is available, and just see the waveforms here, and the bottom one is a voltage waveform. Now you can see there is a small negative voltage beyond omega is equal to pi for every half cycle. for every half cycle, there is a small negative spike, right? Which is not available in the R load condition, because all other things are same. Only thing we have introduced is a L component in the load, but now we are getting a small negative peak. And when the negative voltage is introduced, and when you take average, definitely the average voltage is going to be reduced. Right? This is the concept of introducing R load or dealing with the R load, which is a full wave rectifier. When RL load is when RL is the load, then definitely for the same firing angle, the output voltage, average output voltage will be lesser than the previous one. But this is not applicable for the RMS, because RMS does not carry the quality of the voltage. But for average voltage, with respect to the R load condition, RL load will have a lesser average DC voltage for the same firing angle and the same supply voltage magnitude. Right? If you want to distinctly understand this particular concept, let us increase my firing angle to 75 millihenry instead of 40. I'm increasing my inductor value as 75 millihenry. Now see how the voltage waveform is changing and how the average voltage is getting reduced. Please take a look on the second waveform, not the first one. First one is current. I think now you can see the negative part of the voltage is increasing. When you increase the inductor value, the negative part of the voltage is increasing. So the average voltage will be decreased. If you see the output voltage, now you can see the average output voltage is just 190 instead of 196 or something. Now, instead of 195 or 193 or 192, now we are getting 190 volt. So when you keep on increasing your inductor value, your average voltage will decrease for the same supply voltage and the same firing angle. This is the concept. And with respect to the waveforms, you can see that here the waveform is not in phase with the current waveform is not in phase with the supply voltage. Earlier, whatever waveform of the voltage, that will be followed by the current. Now this is not the case, and the current is rising from zero linearly. Current is rising linearly from zero only exactly from alpha point. Only from whenever you supply the triggering pulse, from that instant only the current is increasing in the circuit. But that too it is increasing linearly because you have your inductor in the circuit. In the previous case, since it is R load, wherever you trigger the thyristor, the current will also reach the corresponding value, a higher value, directly from zero to some value. It will have a steep increase, and once again it will follow the voltage waveform. But here the current is not increasing steeply; it is increasing very smoothly because you have an inductor in the circuit. And moreover, even the voltage becomes zero, you can see the current is still positive. That you can note down here. Even after the voltage becomes zero, the current is still positive. That if you closely look only one particular cycle, you can understand that. Now you can see even after the voltage becomes negative, current is still positive. It means that the current is lagging the voltage, and the positive current is more than enough to keep the thyristor in the on condition. It means that that particular current is greater than the latching current of the thyristor. So because of that, the same set of thyristors, which means the T1 and the T2 is still in conduction even after omega t is equal to pi. It is still in conduction even after omega t is equal to pi. So because of that, after omega t is equal to pi, this supply voltage will become negative. So for a small amount of period, the negative voltage is also appearing across the load terminal. That's why we have a small negative spike in this area, right, beyond 0.02 second. There is a small negative peak, and whenever the current becomes zero, you understand that the current is becoming less than the holding current, so the thyristors are turned off and there is no current. Current becomes zero, and the next set of thyristors are waiting for the triggering pulses at omega t is equal to 30 degree. Right, we are giving alpha as 30. So the next set of thyristors T2 and T4, sorry, T3 and T4 are waiting for the pulses at alpha is equal to 30. And once when you give the firing pulses at alpha is equal to 30, the voltage immediately appears there as per the sine wave, but the current is increasing linearly. Once again, this is because of the inductive effect. And how much angle beyond pi degree, for how much time the current will be available in the positive side, that is decided by the RL combination. We can say that it is a load angle. Load angle is equal to tan inverse of omega L by R. So if you calculate this tan inverse of omega L by R for this particular combination of R and L value, you will get the duration for which the same set of thyristors will be in conduction beyond pi degree, or the current will be staying in positive side beyond pi degree in terms of angle. That is called the load angle. And from this you can understand that not only by increasing the inductor value, for the same inductor value, if you decrease the resistor value, then also you will have an impact on the circuit. Right? By keeping the same inductor value, if you decrease the R value, tan inverse of omega L by R, that will have a change. So then the current will be available in the circuit for longer time in the positive side beyond omega is equal to pi, and then only the current becomes less than holding current. Right? And this method, if you calculate omega L by R for this particular condition, it is coming as 2 pi f. L is 75 millihenry. Omega L divided by R is 150 ohm. Tan inverse of 0.15707. It is coming around 9 degree, right? That's all. Only 9 degree is the load angle. So the load angle determines for how much time the current will be staying in positive, and alpha is the one which decides the firing of next pair of thyristor. So now we can come to a conclusion from this diagram, from this waveforms. When load angle is less than alpha, the even after pi degree, at some point of time the current will become zero at omega t is equal to pi plus 5. Right? I will write all these things in the board now. So the current will become zero at omega t is equal to pi plus 5, and the current will the next set of thyristor is waiting to receive the pulses at next alpha. But in case if alpha is less than load angle phi, then the current will never become zero. The reason, before the current becomes zero, the next set of thyristors will be triggered, so the current will start to rise with in the next loop. In the next half cycle, the current will start to rise. So the current will never become zero during the condition when alpha is less than load angle phi. Right? So, but based on this, there are two operating conditions for the full converter with R load. One is discontinuous conduction mode, second one is continuous conduction mode. When alpha is greater than phi, it is discontinuous conduction mode. The waveform is shown for that particular condition. Right. And if load angle is greater than alpha, or when alpha is less than load angle, the current will be continuous. Right. So now with the same alpha and the same L, I am going to reduce my resistor to 30 ohm. I am going to reduce my resistor to 30 ohm with this resistor value. With this resistor value, right? I am going to simulate now, right? With this resistor value, now I am going to simulate. Let me calculate the load angle here. So omega tan inverse of omega L by R 2 pi F, same 75 millihenry. Omega L is 23.56 divided by R is 30 ohm. So I'm getting 0.7854. 0.7854. 0.7854. I'm getting the load angle is 38. The load angle is 38. Right? So now, if you see the waveform, we can distinctly and we can see the difference very clearly. Right? Now I'm going to check the waveform here. Please see here. Right? Beyond 0 degree, beyond omega t is equal to pi, more negative voltage is available for this particular case. The reason, load angle is increased. Load angle is increased. This is what I mentioned. Not only by introducing inductor L, we can increase the load angle. By reducing the value of R, you can increase the load angle. So up to load angle, the negative part of the voltage will be available across the load terminal, which is shown in the second waveform here. And now you can see the current waveform, which is not at all touching the zero. The current waveform is not at all touching the zero. The reason, before the current reaches the value less than holding current, the next set of thyristors are triggered. So current is rising through the new set of thyristor and it is progressing. So for every half cycle, before the current reaches less than or reaches the holding current value, the other pair of thyristors are getting triggered, because in this condition alpha is less than your load angle. Alpha is 30 degree, load angle is 60 degree. Sorry, load angle is 39 degree. Load angle is 39 degree, alpha is 30 degree. So current becomes discontinuous. And in this case, if you see the voltage waveform, you have more negative voltage. So based on the analysis that we have done, you can understand that the average voltage across the load terminal is just 178. Earlier it was 190 with the R load. It was 190 with the R load, and when I 192 with the R load, and when I introduced a small inductance, it was reduced to 190. But now, when you when compared to the resistance, now the inductance is more dominant. So when compared to the resistor, inductance is more dominant. So more negative voltage is appearing. You have lesser average voltage across the loaded terminal, right? So now with this concept, let me give you the equations for this particular full converter. This is not so difficult. Only thing you have to understand the limit. The inside the equations are going to be very similar like the load. Only differences you have to understand how to write the So this is full converter with RL load, right? And the average DC voltage VDC is equal to now if you see that the voltage waveforms are symmetric. Once again, voltage waveforms are symmetric for any full converter. The voltage waveforms are always symmetric. So it is enough to take average for one particular off cycle. You need not to do it for the full cycle. So right. So it is better. It is good enough to derive the equation for off cycle. So the inside the equation is same. Vm sine omega t d of omega t. The only difference in the limit is obviously the starting limit is alpha. There is no doubt in that. The thing is, for the previous condition, don't assume this condition. For the previous condition, there was a discontinuity in the voltage, right? There is a small negative part, and after that negative part, the voltage becomes zero, and at the next alpha instant, the voltage will appear, right? Beyond omega is equal to pi, how much time the voltage is available, that instant is called as extinction angle beta, right? Extinction angle beta. So let me at least that alone I can draw it here. 1 minute. That particular waveform alone. So when during RL condition, the voltage will start to appear here, and there will be a small negative part, and this will be zero, right? And this is called alpha, and this duration is called beta. So the limit is alpha to beta. This you have to understand. This is a discontinuous conduction mode. So now we should know for what angle this is working. So when you have this particular limit, the output becomes Vm by pi cos alpha minus cos beta. This is discontinuous mode. Discontinuous conduction mode. This is VDC, right? VDC, not VRMS. This is VDC. Vm by pi cos alpha minus cos. For the next one, for continuous conduction mode. For continuous conduction mode, same equations. VDC is equal to 1 by pi Vm sine omega t d of omega t. Alpha is also same, but the limit is, if you see this particular waveform, you can understand that the voltage is available from alpha to pi plus alpha, because the current is still continuous, and at pi plus alpha we are triggering the next set of thyristor. So from pi plus alpha the next half cycle begins. So now we have to take average between alpha to pi plus alpha. So if we do that, then the limit becomes alpha to pi plus alpha, and if you manipulate it, you will get the equation 2 Vm by pi cos alpha. This is for continuous conduction mode. This is for discontinuous conduction mode. This is for continuous conduction mode, and both are for RL load, and the equation is for average DC voltage. Similarly, with the same limits alpha to beta for discontinuous conduction mode and for alpha to pi plus alpha for continuous conduction mode, please try to derive the VRMS equation, which is also very important. Only thing, you have to square this particular part, Vm square, sin square, and the and you have to take the square root. So please do that and get the value of RMS voltage for these conditions. For continuous conduction mode and discontinuous conduction mode, same limits, only thing square the equation and finally take square root for the answer. Right. Please do that, and if you have done this experiment for 3-phase in the lab, I mean for single phase in the lab, please take a look on that. Look at your manual, so that at least study that manual. That lab manual has some good content to understand the single phase full converter. Please go through it, and during the next class we can discuss. You can leave now. If you have any doubts.